Hi, in this video I will talk about representations for G. Remember, in the last two videos I talked about G, the bivariate extreme value distribution function. According to the material I presented, the possible forms for G can be uncountably infinite. But these uncountably infinite forms can be expressed in a unified form or forms, as I will explain in this video. So this video is about representations for possible forms for G. G represents the CDF of a bivariate extreme value distribution. I will talk about 4 different forms. The first one, suppose fx and fy. These are the 2 marginal CDFs of the data belong to the Gumbel limit. Okay. Then the possible forms for G can be expressed as follows. Sorry, this should be S, not Y. The integration is with respect to S, okay? Okay, where f1 and f2 are non-negative functions, and they must satisfy the 2 conditions, that the integral must be 1 and the integral of f2 should also be is equal to 1. So this is the first representation, which says that if the marginal distributions of the data belong to the Gumbel limit, then all possible forms for G can be expressed in this form, where f1 and f2 must satisfy these 2 conditions, right? Okay, next representation is as follows. Number 2. Right. If both these belong to the Gumbel limit again, then the possible forms for G, the bivariate extreme value CDF, can be expressed as follows. Where K is a function that satisfies the following conditions. That the limit as t goes to infinity of K of t must be 1. That the limit as t goes to minus infinity of K of t must be 1. Okay. The derivative with respect to t of must be less than or equal to 0 for all t. Okay, and the derivative of all t, and finally this must be non-negative for all t. So this representation is equivalent to the representation I gave you in the previous slide, right? But it takes a different form though. It involves this function k, which must satisfy these 5 conditions, right? Right. The next representation is as follows. Number 3. And so here the 2 margins of the data belong to the pressure limit. In this case, the possible forms for G can be expressed as follows. Right? Where A is a function from the unit interval to the unit interval, and it satisfies the following conditions: that A of 0 must be 1, A at 1 must be 1, all right. A must lie between these 2 for all W, and finally A must be convex function. I hope you know what a convex function is. If you forgot what a convex function is, I will just remind you. I will remind you over here that a function f, right, is convex, right, if and only if, right, if and only if the second order derivative, right, is positive for all x. So this is one way to determine a function is convex or not convex, right? Okay, guys. I hope you remember this from your earlier years of study, right? Okay. So that's representation 3. Now, next is representation 4. Okay. Suppose that the marginals of G, so this is the marginal distribution of G, is equal to and this is the first marginal, this is the second marginal, also equal to this for y greater than 0. Right? I mean, these, if you may recall, these are the exponential marginals. So let me point that out. What you have here are exponential marginals, right? Now, given this is the case, then the possible forms for G bar, remember G bar denotes the survival function corresponding to G, right? I talked about this notation earlier in the course. Can be expressed in this form. Okay. Where A is once again a function from 0, 1 to 0, 1 and satisfies the following conditions. The first the conditions are the same as in the previous representation. A at 0 equal to 1, A at 1 equal to 1, and A of W must lie between these two for all W, and finally that A must be convex. Okay, so these are the 4 representations I wanted to talk about. Now, just to summarize, the first 2 representations are for the Gumpel limit. The third representation is for the Frechet limit. The fourth representation is when the marginals are exponentially distributed, but we have, or I have not given a representation when the marginals belong to the viable limit. Remember, there are three possible limits according to the ETT: Gumbel, Frechet, or viable. So number 5, if the marginals belongs to the viable limit, then no representation is known for G. Okay? So this is an open problem you may want to work on. Okay. I don't think this will be a difficult problem. It seems to me that it just that people haven't just looked at this problem, right? Yeah. I do not think it is a difficult problem for solving. But okay. Anyway, if you are interested in this area, you may want to look at this problem. Right. Okay. Now, the next thing I want to do in this video is to do an example, just to illustrate one of the representations I gave you, one of the 4. Okay. All right, this is example. The question is that show that this is X, sorry. Okay. So the question is the following, that show that this corresponds to a bivariate extreme value distribution. Now, I gave you four representations. Now, the question is, which of the 4 representations will this belong to? Right? To answer the question, let's first look at the marginals of this. Right? All right. Right, if you put, because this is a survival function, to find the marginals of X, right? You may recall this from much earlier on in the course. To find the marginals from a survival function, you need to use this formula, right? Which is, so if you put y equal to 0 into this, you get 1 minus e of minus x, right? And similarly, the marginal corresponding to y, the formula for this is 1 minus this, and this is, if you put x equal to 0 into this, you get 1 minus, okay? So you see that the two marginals, they are both exponentially distributed, right? So we need to show that G bar that G bar satisfies representation 4, because representation 4 was the one where we assumed that the marginals of G are exponentially distributed. So we need to basically show that that this expression for G bar can be expressed in the form of representation 4. Now let me return to representation 4. So this is the representation number 4, right? So we need to show that the given formula for G can be expressed in this form, where A satisfies these 4 conditions, right? So that's what I'm going to do. Okay, so I'm going to write this formula, right, in the form of representation 4. So we can write the given form for G bar, right, as follows. Okay, you see what I've done? I've pulled out the x plus y outside because I want to write this in the form of representation 4, right? So what this implies is that, according to representation 4, A at y divided by x plus y must be equal to this, right? So in other words, A at w, right, must be equal to theta w squared minus theta w plus 1. Now we must show that this function satisfies the 4 conditions. Remember the 4 conditions. The first is that A of 0 is equal to 1. The second is A of 1 equal to 1. The third is that A of omega must be between max of omega and 1 minus omega and 1. And the fourth is that A is a convex function. So let's start with condition 1. It says that A of 0, which is equal to theta times 0 squared minus theta times 0 plus 1 is equal to 1. So hence condition 1 is satisfied. Condition 2, A at 1, which is theta times 1 squared minus theta times 1 plus 1, all right, which is also equal to 1. So condition 2 is satisfied. All right, now the next condition, we need to show that A of w is between the max of w and 1 minus w and 1, right? Okay, now let me show you how to do that. So this is condition 3. We need to show that that A of W is between the maximum of this, right, and 1. Now this condition is equivalent to the following. The first is that A of W must be less than or equal to 1. The second, that's for all W. The second is that this must be greater than or equal to W for all W. The third is that it's greater than or equal to 1 minus W for all W. Now let me call this A, Part B, and Part C. Now I'm going to show you each of these is true, right? So let's start with Part A, okay, which is A of W must be less than or equal to 1 for all W, right? So in this example, A of W is theta okay. The 1 and the 1 cancels, so you get what? And this is, you can write as and this is always non-negative, less than or equal to 0, because W, remember W is a number between 0 and 1, right? So W minus 1 must be less than or equal to 0, and theta is a positive number. Although I did not say that, I must have said that before. Theta is a positive number, so this is always less than or equal to 0, right? So this is true. Now Part B, we need to show that this is true, right? Which is the same as saying that and this is the same as saying okay, and this is the same as saying that okay, and this is the same as saying that right. Now this is true because W is a number between 0 and 1, and theta, by the way, I should have said that since theta is a number between, the question must have said this, my apologies for not saying that earlier. Theta is a number between 0 and 1, so theta W must be a number between 0 and 1 too. So this whole thing must be greater than or equal to 0, all right? So we have proved Part B, all right? The next thing we need to show is Part C, which is that this must be okay, which is the same as saying that okay, and this is the same as saying that Um, okay. And this is the same as saying that theta w squared plus 1 minus theta w. Okay. Now this is true because theta w squared is greater than or equal to 0, and this is also greater than or equal to 0 because theta is the number between 0 and 1. So this is true since theta is a number between, once again, the question should have said that this is the case, right? So what we have shown is that right, that okay, we have shown that AFW is between these two for all W. Okay. All right. So there is only one more condition that we need to check, right? Which is that A must be a convex function. Okay. Now we know that A is given by this. To show that this is a convex function, we need to find the second order derivative of it. So let's first find the first order derivative, which is 2 theta, right? Now the second order derivative is going to be going to be 2 theta, which is always positive. So hence we have shown A is convex. Hence A satisfies the 4 conditions, right, of representation 4. Okay. So hence the conclusion is the following. Okay. All right, guys. So that's the end of this video. Okay. You should go to the course website. It contains many questions similar to this, and you will also find the full solutions at the course website. So I suggest you practice on those questions without looking at the solutions. And if you have difficulties, you can look at the solutions.